I wanted to share a presentation on what Sensofar as a company gives to the industry, and especially, of course, this presentation has been focused on mainly three of our markets, which are photonics, optics, and semiconductors, that lately have been very kind of interlinked. And well, I will explain a little bit more on that later. So, yeah, first of all, well, in case anyone doesn't know Sensofar, we've been a technological company since 2001. We were a spin-off of the university, and since then we have grown into a worldwide company. Now we have offices apart from our headquarters in Terrassa, in Barcelona, in Spain. We also have direct offices in the US, in Germany, in Asia. And also we have a global network of distributors to be as close as possible to our final customers. So yeah, basically in one phrase, we design and manufacture these 3D optical metrology systems. And yeah, they are mainly specialized for industry, but also, of course, for an R&D labs. Here, well, the unique thing about our systems is that they combine four core technologies in a single sensor. So we have confocal interferometry, focus variation, and spectroscopic reflectometry all inside the same head. And this is kind of the flexibility is what allows us to measure from surface texture, defects, shape, critical dimensions, and even transparent film thicknesses. And well, we go from the millimetric range more or less to the subnanometric in terms of vertical resolution. And well, most importantly, or I wanted to highlight here that all the hardware and software are developed in-house. So thanks to that, we are able to optimize and kind of fine-tune all the system to provide the best possible performance and user experience to the final customers. Here, well, we offer mainly two kind of systems. So first of all, we have tabletop systems, and well, in these ones, the users can create or define the recipes to measure. They can program the system if they want to go automatically to different locations, different samples with just one click of a button. And then, well, all our acquisition software is linked. The user decides how does he or she want to analyze their data, either manually or fully automatic. Depends on that, they use one of these. And well, basically the goal is at the end to have a report, PDF, pass and fail report, Excel file, whatever it is, to visualize and analyze all this kind of data from, again, from one sample in particular, more like an R&D step, or from a whole batch of samples in production. We have systems like these running in fabs 24/7. So we are more than prepared to provide a solution for daily for production. So the other kind of solution we have is even more automated and more focused for production. We have this kind of integrable heads. So we just take the core technology that we have, which is the head with their optical design and all these technologies, and then we give it to the customers so that they can integrate their hardware, and integrate the head into their machines in different ways. So sometimes there's kind of an integrator that is dedicated to this kind of solution. The customer just asks what their final solution looks like, and then we work with an integrator to make this happen. But basically what we provide is just the head and then the software development kit, this SDK, so that the customer or the integrator can design their own software interface that can command from a separate computer. They can link also to the analysis software. It's a very kind of customizable way to do that. And here I wanted to show just a few examples of our heads integrated in different machines. In these particular cases are from the semiconductor industry, but as you can see, the final setup can look very differently. But these are fully integrated machines, very close to production, sometimes inline production, to analyze all these kind of things that I was talking about: surface texture, defects, critical dimensions, and so on. Okay, so now I wanted to jump into the application side. So here, let's start with optics and photonics and what we measure and what we provide value to the industry. First of all, we can measure optical fibers, for example. So we characterize from the lateral dimensions of these optical fibers, waveguides, to this kind of height values or depth, even sometimes through the transparent materials. Also, we measure gratings and 2D photonic crystals. We can measure down to basically the Rayleigh criterion, so the optical limit, diffraction limit, 300 nanometer spacing, though it's quite challenging, of course, at these steps. But yeah, any kind of geometry for this kind of photonic crystals or gratings, we can measure in the samples. And then, again, depending on the customer, we can analyze it more like manually or fully automatic with a software that automatically detects all the critical features and then reports the pass and fail. Also, we measure, of course, lenses and mirrors, basic optics stuff. We can measure from the form itself to the roughness measurements. Here, I want to highlight the precision and the accuracy of our technology. So we can go down to the sub-nanometric level. Here we have a average roughness of 0.5 nanometers. And this is precisely measured thanks to our interferometry techniques that can go down to 0.01 nanometers of vertical resolution. So that's very critical as the previous talk that we were talking about the need for precision and the need for calibration and so on. Here is very critical. And in the latest last years, we have been optimizing our algorithms and our techniques to be able to provide the best vertical resolution and best accuracy for this kind of market. And yeah, also forms of lenses. We are very specialized in the fields of micron range lenses. So with 100 microns diameter, typically tens of microns in height. These are well, probably all the audience will know that have been used more and more lately, thanks to the integrating photonics into the semiconductor industry. And well, related to that, we also measure micro lens array. Basically, same principle. We measure again shapes and different parameters from these arrays that are being used for this kind of transmitting and connectors to the semiconductors. Jumping into the semiconductors here, I won't bore you with all the things that we do here. We do a lot of stuff and a lot of applications, but here we have a wide overview of all the processes that are related to the semiconductor fabrication, from the wafer itself to the front end processes and the back end packaging and all related processes. I wanted here just to highlight very briefly a couple of applications. We measure from the bare material, bare wafer, bare crystal that are used either before or after polishing. And again, we are using the interferometry techniques here to measure as precisely as possible materials like silicon carbides, diamonds, perovskites, of course, bare silicon and silicon oxides. Here we also measure, related to the semiconductor, we can measure photolithography masks, especially these ones in particular, I think, are from the extreme ultraviolet photolithography mask, in which they just resemble some kind of steps. So for us, it's even easier to measure in this way. They were characterizing these hundreds of nanometers height structures that are used to redirect the light into the masking process for the semiconductor and the transistor manufacturing. Also, we are checking edge profiles even after wet or dry etching. It really doesn't matter. We are checking at the profiles here, the different angles, different heights and critical dimensions. And of course, at the very end of the process, we measure bumps, general bumps, electrical connections, flip chip connectors, bumps, wire bonding as well. So we have a bunch of different software plugins that analyze these kind of topographies and files, and we are able to detect individually all of these little bumps and detect if there's any kind of defect, any error, any thing that may be a problem in production. And now jumping to advanced packaging, this has been a hot topic lately, and I wanted to bring it here to this presentation because in some way, both advanced packaging and this kind of heterogeneous integration techniques are bringing photonics and optics together with semiconductors. So here, this if someone doesn't know, this is kind of new strategies that manufacturers have been taking in terms of increasing the density of chips, more well beyond Moore's law, and also kind of reducing latency for high performance computing and so on. So in here, there are very kind of specific structures that we check for manufacturers. First of all, microbumps. So already we have seen bumps. It's basically scaling down to these kind of little bumps that are connecting the chip with the kind of interposer, so middle layer, not the substrate. Then we have through silicon vias, so these are holes directly through the silicon. Sometimes also you will see through glass vias. We also measure that depth and critical dimensions of the holes. Then we check wafer glue, so to bind this together, the different layers, these manufacturers use some kind of glue for these chips. And then we measure the profile and the different possible defects and widths over these kind of structures. And of course, the substrate. So this is from standard PCB structures to the latest high-tech redistribution layers. We check the widths, heights, and critical dimensions of these kind of traces, trenches for applications like the fan-out panel level packaging. And finally, we have heterogeneous integration, which is even more complex, and it's integrating different components into the chip, doing this kind of system on chip, system on wafer kind of structures. Here we check co-package optics. So again, it's very similar to the applications that we have in optics. We measure waveguides and fiber and optical fibers related to this very high bandwidth applications for high performance computing, for AI applications. All of you have heard in the latest years all these kind of applications. Also, new materials have been integrated into the chips themselves. Again, silicon carbide, gallium arsenide, gallium nitride. This basically is for high power applications. And then we have microelectromechanical systems that are, again, being introduced sensors, actuators into the chip to provide a package that is as functional as possible. And finally, very related to the previous applications, we measure microlenses, specifically those that are being used to try to connect and to bring this kind of photonics connectors inside the silicon chip or the transistor layout. So that is very important here to check aspheric and spheric microlenses, for which we already have some kind of already built plugins to analyze this. So yeah, one final question for you is that I wanted to point out what challenges can we solve together. We're always happy to explore new opportunities, to discover more about the latest discoveries that are being used in the industry and in R&D. So yeah, if anyone has any application for us, we are open to hear that, and our applications team will be happy to hear from you at sales@sensofar.com, or of course now in the questions and answer part. And yeah, if anyone wants to know more about our technologies, we have a bunch of different materials and webinars on our website. So yeah, thank you. And now I'm ready for your questions.